All right, welcome back, everyone. Today, we're shifting gears a little bit, and we're going to talk about time series. Come on. Oh, sorry, no. Stretching. Yeah, sounds good. Which, if you think about what we have done so far, we modeled all kinds of snapshots of things. We haven't worked with time yet. And this might be, you might wonder, when are we going to do this? Because, as I was arguing earlier, time is an essential ingredient when trying to establish causal relationships, which is one of the things we always want to try to do if we can. Yet we haven't really talked about time. So today, we're going to talk a little bit about time, and you're actually hopefully still having devices with you because we're going to try a small hands-on thing again. And I would like us to read a couple of papers for Tuesday, which I will post today. So if anybody is so willing and interested, I would appreciate it if you would sign up to present on Tuesday. Sorry about the short notice. Hopefully it's not too short.
That's fine. More than 2 days.
Okay, weekend doesn't count though.
I like that.
So it's still kind of still 2 days. Yeah, kind of borderline more than 2 days if you use the weekend. Okay, so first off, I want to very briefly tell you a bit about just time series in general, and then I'm going to tell you about one of the most amazing time series analysis techniques ever invented. So simple and so beautiful, and we're going to play with this hands-on. But first, also separately, a few of you have started sending me bug reports or questions about the FC data set. I'm looking into this after class because I didn't have time before. You just send me, and I'll post my answers and whatever updates and whatever I find, I will send an email to everyone so you all know what's happening. If I need to update something in the data, I will send a new version. I'll let you know. If you find more weird things, please tell me. I will do my best to fix them swiftly. Okay, so let's talk about time series. So time series is basically just observations of anything collected over time. Here is one simple example. This is a time series of beer, let's say, production in Australia over time. What do you see when you're looking at this chart?
There's spike.
There are spikes. Yes. One thing. Yes. Long.
Well, spikes probably means seasonal.
Yeah, so it's one common characteristic you will often see with time series data. This artifact called seasonality. Right? It's very natural if you think about it. There's probably more beer production when the weather's warm, when people drink more beer. It's also probably more ice cream production when the weather's warm and when people eat more ice cream, and less of either one of those in the winter, for example. It's very natural to expect that there'll be increases that correlate with seasons or weather or something. And the cyclicity of this can vary. It could be at a level of hours in a day, it could be at the level of weeks or months, or who knows what, right? It could be anything really. But the point is the patterns will repeat itself of ups and downs because of some external factor like this. Here it could be weather. And what else do you see?
That's like this once a year. The frequency so.
Looks like it. Yeah, looks like it. Looks like there's about 5 or so spikes between 2 consecutive points on the x-axis. Yep. So there might be yearly spikes in the summer or something. Yep. What else?
The tendency is to increase.
Right. So over time, increasingly more, whatever, production of beer. Yep, sound good? Okay, here's another one. Monthly airline passengers. what's different, or how do we interpret this, and how does it compare to the previous one?
Yeah, I was probably gonna say something. Yeah, it's the seasonal spikes again. The spikes are like greater during the on season.
The buffer music.
So seasonal spikes, yes, but somehow the magnitude of the spikes is not constant anymore, right? Like the previous one, the difference between highest point in the year and lowest point in the year was about the same. That's not the case with this one.
We have an increasing on the beginning of the year. Then another jump.
Right. There's some irregularity, and so it's not as clean a spike as we had before. There's more, I don't know, spikiness to the spike. I agree with this. And also, note how it starts with being very narrow and it sort of gets increasingly wider. So we're calling time series that look like this or behave like this. We're calling them multiplicative. And we're calling the ones that look like the other one additive. To sort of guess why we're doing this. But let's try to figure out how we might separate these different patterns that we've observed so far. So one thing we could do is to try to detect just overall trends. That could be one kind of question that you're often asking. What is the overall trend in this time series? And visually we can tell that it's increasing, but how might we model this? Ideas? Very easy, simple approach. Moving average. Okay, and you see this here, moving average, and I think we take 4 consecutive points into account or something when computing it. And that gives us that solid line you see there in the middle, which captures the trend in this time series over time. Sound good? So we could plot the trend independently and treat it as sort of a smooth out version or something, and do an analysis on the trend alone. Here's what the trend looks like. We could do the same thing with the airline data, very similar, and we could look at it separately and interpret it and so on. Okay, now let's say we have figured out a way to model the trend. We could take the difference between the actual observed values and the trend, much in the same way I decomposed observations of typing speed into average typing speed and whatever's left over before. Similar idea, kind of extracting the mean, if you will. And you're left off with something that is now centered around 0, ideally. That makes sense? And I can do the same thing for the airline data, except now instead of subtracting it, I divide by it, which is why we call this one multiplicative and the previous one additive. Make sense? So now, these have also normalized their roughly, there's some variance, but still normalized roughly their range. Okay. Now the spikes, the difference between the high points and the low points of the spikes becomes relatively uniform. Okay, good. So here's the way, we further model the seasonal effect, right? We see it going up and down. And, we get something like this. We can do the same for the airline data. Okay, so after explicitly modeling the trends and explicitly modeling the seasonal pattern, we're left with just whatever's left over, right? Because obviously, you know, it won't be a perfect fit of just the trend and the seasonal pattern. So there's some error term that contains whatever's left over in this time series for each of the observations. And ideally, this is centered around 0. And if you've done a good job with capturing the trend and the seasonal effects, it's also relatively uniformly distributed around vertically around 0. Kind of like the residuals for regression before. Okay, so you know this sort of looks okay. You could do the same thing for the airline data, and this also looks relatively okay. So that's sort of you're happy that you've figured out how to model this. And the idea is that, you know, at any point in time, you can reconstruct the original observations. For beer, you can reconstruct them by adding together the trend, the seasonal component, and whatever's left over, because this was an additive time series. So you just add everything up, you end up with the same original observations. And for airline data, you multiply them.
Why do you have to multiply by random? Because I thought random. I understand why you have to multiply by trend and seasonal. Why do you have to multiply random?
I guess it's an assumption you do for modeling. You're saying, you know,
or like how is random computed again? Can you scroll up a little bit?
Well,
is it like by dividing? Or
basically,
by dividing that
you just reconstruct, yeah. But I guess you could have said, you know, maybe I only apply the random to the trend component or something, and not to the other one.
Or like the model, trend error times seasonal error, and then plus random.
You could have done something. Yes, you could have done something like that. But I guess here the multiplication gives you this increasing spread the farther right you get, which more accurately captures the data. Okay, so this is all great. You've done all of this by hand, and you don't actually have to, because there's libraries that do all of this for you. There's at least 2. One is called TS. This is built into R. You could just call TS by default. You don't have to load a library for this. It's built in. So for beer, you could say, you know, create a time series object of that original data with frequency equals 4. This might be quarterly data. I think you have 4 quarters per year, which is why frequency equals 4. And you decompose it, and it's additive, presumably, and you get all of the different components. You get the trend and the seasonal thing and the random leftovers, and this nice plot that shows you everything in one. So this was the original data we started from, the beer production, which had a trend component, a seasonality component or a seasonal effect, and whatever is left over, random part. Pretty nice. It's a way of, you know, modeling and understanding this data. The same for the airline data, except now it's multiplicative, and these were maybe monthly observations instead of quarterly, hence frequency equals 12. And you do all of that, and you get something very similar, you know, original data, trend, seasonal effect, and points. And so same with this STL library. STL stands for seasonal, trend, and I don't know what L is for. S for seasonal, T for trend. I don't know what L does. Anyway, there's another library you can load that does all of the same things, and reduces all of these components for you, and then you could work with them separately, and it's all very nice. Long.
This is seasonal time series by Lowe's, LOE.
Okay, so that's instead of a moving average, it does something else for computing the trend. So maybe it looks smoother or something like that. It's a different way of computing the trend.
When you look at the reminder, can we infer that it's something slightly or that's something different on that year or on that?
Right. So the idea is that you can inspect the remainder, the random part of this in much the same way we were looking for patterns in residuals before, because this is essentially residuals. Residual just means whatever's left over. That's what this is too. So you can see, how well does this two-component model, having a trend and a seasonal effect, how well does that capture the original data? You see kind of how much pattern there is in the residuals. And then if there is some that's clearly observable, you probably should do more than just have the two elements.
Yeah, but my question is more, if I have a big spike on one of those, can I say that that can be an outlier?
Oh, could be, yes, yeah, sure, yeah. It's a way also to help you inspect the data and see if the course instructor made a mistake in the CSV file that was shared, or something else happened.
Or, for example, if you have big sport event that year,
Yes,
so year,
yeah, World Cup maybe was
Yeah.
hosted in Australia or something. Or maybe more rugby or
so
something.
we will see a spike on this really,
That's right,
because the trend will be more or less the same.
yes.
Do you know what those blocks are for on the side?
You mean these ones, right? No.
Okay.
But I know how to find out. You can study the documentation of the STL library or function, which is this one. Read the docs. Maybe you could just ask ChatGPT. Okay, good. So this is one of the simplest possible exploratory analyses you can do on time series data as a way of understanding what's going on. And usually also when it comes to modeling things, which we'll do in a minute, you probably want to focus on trends, because usually when you're looking at time series data, you want to reason about trends over time, most commonly, which is why doing this kind of decomposition where you remove seasonality effects can be useful, because it allows you, it gives you cleaner data to then do some analysis and modeling on. So this is often, pre-processing for something that comes downstream, and I'll show you one example in a minute. That makes sense? And obviously, how do you know to look for seasonal effects? You gotta have a. There we go. Very good. You've been sufficiently brainwashed. I love it. Thank you for playing along. Okay, yes, I'm good. All right. So now let's get to the interesting part. The interesting part is the following. We're going to talk about this technique called interrupted time series analysis, which is very powerful. The idea is very simple. Let's say, imagine the following data. These are hospital admissions in Italy for acute coronary events. So people that had to be admitted to the hospital because they had some heart issues. Okay. And you can see monthly data, I think, over time from Sicily, maybe this is right, over the course of some period. Okay. Now, the interesting bit here is that in 2005, they introduced a new policy. There was a ban on smoking in all indoor public places. And, arguably smoking is correlated with all kinds of bad outcomes, including maybe coronary events. So you might be asking yourselves, one of the most standard questions people ask when doing research like this, which is, has this policy had any effect? Has this intervention had any effect at all on some outcome that we care about? Right? You introduce a new policy, you have some intervention, you want to see if it made any difference. Right? Looking at these observations, what would you conclude, or how would you think about this? Yeah, Ian?
there's two ways I see you could look at it. One is it seems to be increasing a little, and then it stays the same. So maybe it didn't help. Another way to look at it maybe is it's increasing a little, but it didn't increase more. So maybe the fan didn't help. But the data seems pretty scattered, so it's probably hard to conclude.
Yeah, I'm good. Elizabeth?
Another thing with that is, I mean, if they banned smoking in 2005, like you're not really gonna see any effects until later. So I don't know that it's really gonna help with acute pulmonary events in this time frame. Right?
So acute means what, sudden as opposed to chronic? What does it, which one is the one that's there forever and which one's the chronic is the one that's there forever? So acute is the more rapid response one?
Yeah.
So maybe things like blood pressure and stuff like that,
Okay.
like spikes in that might take less time to observe. Which is maybe why the question made sense for, this is for real, this is real data. I'm not taking this time. Taylor.
I mean, this also does make a lot of sense because if I can't smoke indoors, I'm just gonna smoke outside.
Yes, smoke outside. But you know, by smoking outside, the people in the room that you're smoking next to don't get, you know, secondhand exposure or something.
Right.
So you know, maybe they are the ones that are benefiting potentially from this policy.
Right.
Yeah. Luis?
Well, just looking at it, I cannot see any pattern here. But what I'll do here, if that's the only data that is available, would be split the data into two groups and model the two trends separately. And then compare if there's a change in the trend before and after the smoking ban.
Okay, so Luis is an overachiever. That's a great idea. If you're lazy like I am, you could maybe just start by comparing literally the means of the two groups, for example. That's maybe the easiest, simplest thing one could do. You know, are there on average more of those things before compared to after? It seems like a very natural first kind of analysis to do. And I don't know, I haven't done the analysis here. And you're right, you know, if you want to be a little more precise, which is, and to make this more interesting, you might start looking at trends. So here's the way to think about this. The line up until the policy is the average trend in those observations. You know, could be computed with a simple linear regression model. Okay. The line in the gray area, the red line in the gray area, is the trend considering only these observations here. So, you know, linear regression of these points after the policy was introduced. And here's the, you know, billion-dollar argument. Okay, the argument is, had there not been the intervention, the policy change, one could reasonably expect the trend before the intervention to have continued in the same way. Because why wouldn't it if nothing changed? I mean, the counterfactual is no policy change, no intervention. Right? So, you know, the dotted line here, dashed line, whatever, is maybe your counterfactual, is what would have happened had the smoking ban not been introduced. You buy it?
Yeah, we would expect that the trend will be the same.
Because, you know, why wouldn't it? Why? Let's talk about this for a second too. Why wouldn't it? Why wouldn't it be the same? So again, no policy change, right? That we eliminate by construction. Is there any other reason why the trend might be different?
I mean, there's gotta be a million, right? There could be like PSA announcements on TV. that are saying smoking's bad, just as more.
Okay, great. So this is key here to the causal argument, right? There could be, hypothetically, other things that happened at the same time. Right, so for the counterfactual, I only eliminate the actual observed intervention, the one I'm studying. I eliminate, the policy, the new policy. But maybe there are other things, not the new policy, right, that coincidentally happened around the same time. That makes sense? So that's one limitation of this. Right, you sort of have to, if you want to make a really strong argument, you have to argue that there were no plausible ones, at that time, or that somehow you've eliminated them. You see this? But short of that, which I agree is important, short of that, this is a very simple and I think beautiful argument for computing the effect of this policy, which now then you can reason in two ways. You can reason about, maybe immediate effects, if that's plausible, right? And, maybe per this estimate, there was some significant drop in values of the outcome immediately following the intervention. So changes in level, you can reason about. Similarly, you can reason about changes in trends, like you were suggesting in the first place, which again is also very informative and very powerful. And I guess here, the trend is maybe ever so slightly less steep than the counterfactual was. So they keep going up over time, but maybe at ever so slightly lower rate or something than they would have otherwise. Right, so conclusion here could be, you get an immediate benefit, maybe in the short term, and you lose it gradually over time, but at a slower rate than otherwise you could have expected. That would be one way of interpreting this. Right. So this is called interrupted time series analysis because there's this interruption point that in this case represents some intervention, some new policy, something. Interrupted because you separately model the two time series to capture these trends. Okay, yes. So now let's try to do this for real. Let's see what this will look like. I will post in our beautiful Slack channel a CSV file. There we go. Okay. What this is basically this fake data set that, think of this as values of, whatever the outcome was, acute coronary events over time. And there was some intervention, presumably at time equals 100. So this is the kind of data you might just collect, in the wild, right? You have measurements of some variable of interest over time. Okay? And that, there was some intervention that you're studying that happened, in this case, conveniently in the middle of this time window. That doesn't really matter. So the file I gave you has values of, X and Y mirroring this plot here, I think. Unless I did something wrong. Okay. So now question to you, and topic of this exercise, purpose of it, is how might you model the change in level associated with this intervention and possible changes in the two trends, changes between the two trends.
In this case, we have two linear regression.
In a single model, yes. One joint model, one model. That's the assignment. One model, linear regression model, to capture changes in level and or slope. Okay. Yes, there was, let me talk about this for a second. 5 minutes, I want to tell you about. Could be. Let's see if it makes sense. Let me tell you a bit about how to do this. There's, turns out, at least 3 ways in which you could do this jointly in a single regression model. So I lied to whoever I said there's 2. I found a third one in the meantime. Okay, so here's the idea. So here's the idea. X is what I gave you. Right? I gave you time, and it just goes, goes from 1 to 200. Okay? You can do something like this. You could do, okay, step back. We need a few more things, right? So if all we look at is the value of X and the value of Y, we don't have enough information to model all these things together. We need more things, and I've seen most of you come up with additional variables to help you encode that. The critical, most important thing you need to know is if you're before or after the intervention. You need a way of grouping your observations into pre or post treatment. So I've seen people come up with a binary flag, a Boolean. For example, this one here, that is false in the second half, sorry, in the first half, or 0, and it's true in the second half, or 1, whichever. It doesn't matter how you do this, but you do need some kind of flag. Could be anything, but you need a flag that tells you if you're before or after this intervention. Because this flag acts as a moderator or mediator, whichever one of those, I still can't remember. Okay? Acts as that thing. Because depending on the value of the flag, the strength or shape of the relationship between X and Y changes, which is what we're seeing here. Depending on the value of the flag, left-hand side versus right-hand side, the shape of the relationship between X and Y changes from positive to negative with some slope. Okay. So, this flag is whichever one of those we agreed is the right one that's moderating moderating. I always get confused. Which one was it again?
It's moderating.
Moderating, the one that changes the strength. Okay. So a model you could do is X. Oh, come on. X times flag.
Oh, this is a very good marker.
We'll save this one. I promise I have good markers in my office. I just always forget to bring them. There's one way, right, of modeling, because there is an interaction. Interaction term means, you have a moderator that changes the shape or strength of the relationship between X and Y, depending on its value. Right? This is one way of doing it. And now, if you do it this way, you know, you'll get three coefficients, right? You get one for X, you get one for flag, you know, there's a beta, and then you get one for the interaction between X and flag. Okay, and then you get an intercept too at the top. Right, you get four coefficients in your regression. Right? So the intercept is the value of Y when everything else is zero. Right, so it's this point here. Then for every unit increase in X, assuming everything else is at its default value, meaning flag equals zero, probably, meaning left-hand side. For every unit increase in X, the estimated coefficient is how much is the slope of that line, okay? The slope of that line for the default value of flag, which happens to be left-hand side here, okay? Which is the slope of this line, which is this beta. Okay. Alternatively, you have to think about, you know, the flag also has the coefficient. You could think about that. So that value is the value of Y when everything else is zero, right? Meaning when X is zero, and you're on the, sorry, so going from flag equals false to flag equals true is this value when X equals zero. And then the coefficient for the interaction tells you how much the slope changes when flag goes from left-hand side to right-hand side. This is one way, there are two variables, or one additional variable, one way in which you can capture all three of those things. Because I can capture the original slope, the change, and the change in slope after. The one I have here on my slides is slightly different. Okay, so if you know, interactions can be a little confusing to interpret sometimes, if you're not used to this especially. So a maybe more understandable way of modeling this is the following. I create an additional time counter, an additional variable here. The one I have is zero the whole first half and only starts counting in the second half, which is what you see here. So now I can have a regression with all three of those, no interaction term, right? Just a regression with all three, you know, time and the flag and this additional counter I just introduced. And as it turns out, these coefficient estimates map to what I have here on the slide. So, you know, the counter for the beta estimates is the slope on the left-hand side. Okay. The gamma estimate is the change in level, right? From going from flag equals 0 to flag equals 1, which is this thing here. And the delta estimate is not the actual trend after, but the change in trend after, change in slope after. So you add them together in this case to interpret. The actual slope of the line after is the sum of both of these, because both of these are counting at the same time, but in this specification. Alternatively, still, I've seen maybe how change this to having a counter that only counts in the the first half, and then is zero. And similarly to this one, a counter that is zero in the first half and only counts in the second. Okay. And then you could do that too.
But all those coefficients will be the same.
No, all of these will give you slightly different coefficient estimates. All of these, yes.
Because I see beta being mapped.
Forget about, call it something else. Yeah, the actual beta is confusing here.
So
Here, I mean, here when I say beta, I mean specifically this beta in this specification of the model, the coefficient for time. It's likely actually that all three of these would give you consistent estimates for time because time always starts in the same place and goes up in the same way. I think all three examples I gave you are likely to result in the same estimated coefficient for the X variable, but the other ones will be different.
So for the flag, the second there, the coefficient for the flag will be that same coefficient as well, right? That difference.
That makes sense too.
And the third one, the interaction, will be the different slope. So that's omega or whatever, that will be negative and greater than beta
Yeah, so you can
in the that slope.
model the actual second half slope directly if you do the how approach, which is stopping the first counter at the intervention. So then the coefficient for this third term would be the actual slope after, I think. Or you have to add them together if you do this approach here, or I think this is slightly different still.
I think that's just delta, no? X times Y.
X times flag, this thing is
I think this is
Del-
delta.
Yeah, that's what I was saying.
X
It's
times flag is itself.
I think it should give the same coefficient.
X times. I don't know if that's true because so writing this out would be, let's call him something else. What's your favorite letter? A1. A1. So much for the good marker. A1 times X plus A2 times flag plus A3 times X times flag. Okay, so that gives you A1 plus A3 flag times X plus A2 flag.
There's
Right.
also an A0 in there.
Plus A0. And that's right. So so you're asking if you're asking what is A3, right?
Mhm.
And if A3 is the same as delta.
Yeah.
I don't know if that's true.
It should be, because if the flag is one, then it's just A1 plus A3 for the right hand side.
Flag is 1,
Then this thing, it's just beta plus.
A1 plus A3. Yes. Yeah, that sounds right. Okay, good. Very good. Yeah,
So it's all the same model.
yes. Well, yes, except you don't model the interaction explicitly, you fake it in this way.
Right. It's just a way
But
of
in the end, even if the model have different coefficients, the prediction will be the same.
Has to be, if you're
Yeah,
doing it
what-
right. It has to be, right? All of these models should perfectly capture this data. Well, perfectly, should capture this very well. There's some noise, obviously. All of them should be equivalent, right? but how you interpret them is slightly different depending on the specification. Right? So that's really the hard part when doing this kind of work is, I guess, A, figuring out how to specify this in the first place, but B is interpreting these coefficients because they're slightly, that the interpretations changes slightly depending on the specification. So, to your earlier question of the president asking how worthwhile was this new policy, the answer is always the same, but how you arrive at it can be slightly different. So here you would say, the policy resulted in some immediate decrease in whatever, this was. And also over time, things evolve differently. Okay, so last thing, sorry for staying over. Why am I insisting on doing all of this in one model? Like, why do I want to overcomplicate this and do everything in one single regression? Why do we do multiple? Why do we do regression in the first place? Multiple regression.
Assuming whether the intervention is statistically significant.
Yeah, no, not enough. We could do that in a bivariate way also. But what's the benefit of a framework like this with multiple variables?
Because you can see the effects when the others are constant. So
Yes, but in this case, I don't have any interesting ones. So also not good enough. Why did we do multiple regression as a kind of modeling approach in the first place? Because it allowed us to,
Build a theory.
well, yes. Well, it's good. Yes, the safe answer with me. Yes, thank you. I'm becoming a meme.
It lets you analyze each variable in isolation, taking the others constant.
Yes, I think that's what Luis was saying. Okay, so it's that, but imagine now that in addition to measuring just the outcome, right, I could also measure, control variables for all kinds of other things. That's the key. Right, so now I have a framework that allows me to model the outcome as a function of time and policy change and control variables, which is sweet, right? Because, I can be more confident in these estimates of the policy on the outcome while controlling for who knows what that I'm not doing here in this example, right?
Even do that once.
Not if I do only, policy and outcome, like bivariately. If it's just, outcome as a function of policy, but nothing else. By construction, I cannot control for alternative explanations. Right.
From a model point of view, the policy is just one more control variable, right?
Yeah. Yeah, but it's the one that I happen to care about the most in this case. So really, that's the key, right? The multiple regression formulation of anything allows you to plug in control variables to account for plausible alternative explanations that you happen to be able to measure, because otherwise you cannot plug them in. So it's not perfect, but it's something. Right, I'll leave you with this. Thank you for your patience.